This is the EdExcel AS Level Maths Paper 2 from the 2024 series, and in this paper we will be taking a look at the statistics module. Question number 1. A coach recorded the heights of some adult rugby players and found the following summary statistics. The median is equal to 1.85 metres, the range is equal to 0.28 metres, the interquartile range is equal to 0.11 metres. The coach also noticed that the height of the shortest player is 1.72 metres. 25% of the players' heights are below the height of a player whose height is 1.81 metres. Draw a box and whisker plot to represent this information on the grid below. To begin with, if we know that the height of the shortest player is 1.72 metres, that means the minimum value is 1.72. And if we show this on the box and whisker plot, we have 1.72 shown here. If we know 25% of the players' heights are below the height of a player whose height is 1.81 metres, that means the lower quartile is equal to 1.81. And if we show this on the box and whisker plot, we have the lower quartile equaling 1.81. We are told directly the median is 1.85 metres. So the median, 1.85 metres, can be represented on the box and whisker plot here. The upper quartile is equal to the lower quartile, 1.81, plus the interquartile range, 0.11. So adding 0.11 to 1.81, we find the upper quartile is equal to 1.92. So we have the upper quartile being 1.92. To find the maximum value, we need to add together the minimum value with the range. So, the maximum value is equal to 1.72 plus 0.28, which is equal to 2.0. So, showing this on the box and whisker plot, we have 2.0 shown here, and therefore here is our completed diagram. Question number 2. Keith is studying the variable daily mean wind direction in degrees from the large dataset. Keith summarized the data for Cambone from 1987 into 4 directions A, B, C and D, representing north, south, east and west in some order. So we've got the direction A, B, C, D and the frequency of A, B, C and D. Part A. Using your knowledge of the large data set, giving a reason which direction A represents. Now for part A, we have here a map of the UK with the various towns shown in the large dataset, and we've also got a compass here. Now, from the large dataset, we know that the daily mean wind direction is averaged over the 24 hours from midnight on the date given, rounded to the nearest 10 degrees, and the direction of the maximum gust is the direction from which the wind was blowing when the maximum gust during the hour commencing at the time of entry occurred, and is measured in degrees from true north. So, Keith has looked at the large dataset at the daily mean wind direction column and converted the angles of the wind direction given in degrees into north, south, east and west. In other words, anything from 145 degrees to 135 degrees is approximated as east, and that's because we have 45 degrees going from north to east, and so northeast to southeast, that's 90 degrees in between them, gets us to 135 degrees. So northeast to southeast goes from 45 degrees to 135 degrees. And we also know that Camborne, as shown here, is in the southwest of England, and therefore it is less likely that wind will come from the east. If we take a look at the summarised data, we have A equaling 22, B equaling 48, C equaling 56, and D equaling 58. The 22 is the smallest amount from all these, and therefore, as we know that it is less likely that wind will come from the east, we can conclude A would represent east. The entry for Herne on the 27th of September 1987 was 999. Part B, state giving a reason what Keith should do with this value. If we take a look at the Herne data from May to October 1987, on the 27th of September 1987, we see we have a value of 999, and typically the values within this column go from 0 to 360 degrees. So, as the wind direction should be in the range 0 degrees to 360 degrees, Keith should remove this value. Question number 3. Customers in a shop have to queue to pay. The partially completed table below and partially completed histogram opposite give information about the time, X minutes, spent in the queue by each of 112 customers one day. No customer spent less than 1 minute or longer than 8 minutes in the queue. Part A, complete the table, and then for Part B, complete the histogram. To begin with, let's find out the class width of each of these intervals. Between 1 and 2, we have a class width of 1. Between 2 and 3, we have a class width of 1. Between 3 and 4, we have a class width of 1. Between 4 and 6, we have a class width of 2. And between 6 and 8, we have a class width of 2. Here is the histogram that's partially completed. We have the minutes and the frequency density. We've been given the bars for the interval 2 to 3 and the bar for the interval 3 to 4. We know already between 3 and 4 we have a frequency of 13. So what we can do is find out the frequency density by working out the frequency divided by class width. In this case, we have 13 divided by 1, which is 13. And therefore, we can form a scale. We know up to here we have 13, which means up to here we have 10, here we have 5, so we have 5, 10, 15, 20, 25, 30, etc. So we have our scale shown here. For the bar with the interval 2 to 3, we have a frequency density of 25. So we can add that to the table shown here. And if we know the frequency density is 25, the class width is 1, that means the frequency will be 1 multiplied by 25, which is 25. For the frequency density from 1 to 2, we have a class width of 1, a frequency of 64, 1 multiplied by 64 gives us 64. So the frequency density of the interval 1 to 2 is 64. Now, for us to find the missing frequency of the bar 4 to 6, we know we have 112 in total. So if we do 112 subtract 64, subtract 25, subtract 13, subtract 3, we get 7. Meaning, for the interval 46 we have a frequency of 7, and if the frequency is 7 and the class width is 2, 7 divided by 2, which is 3.5, is our frequency density for the interval 4 to 6. For the interval 6 to 8, we have a class width of 2, a frequency of 3. To find the frequency density, 3 divided by 2 is 1.5. So the frequency density of the interval 6 to 8 is 1.5. With all of this given information, we can now complete the histogram. So for the interval 1 to 2, we have a frequency density of 64. That is shown here. For the interval 4 to 6, we have a frequency density of 3.5. That is shown here. For the interval 6 to 8, we have a frequency density of 1.5. That is shown here. So with part A, we have shown the completed table above. That's here. And for part B, we have our completed histogram shown here. Ting decides to model the frequency density for these 112 customers by a curve with equation y equals k over x squared, where x is in between 1 and 8 and k is a constant. Find the value of k for part C. Essentially, the area under the curve is equal to the total frequency. The total frequency is 112, and we can sort of think about that with our histogram. So to summarize the above statement, we would have the integral of k over x squared with respect to x between 1 and 8 equaling 112. And that's because the total frequency is 112. So integrating k over x squared, we end up with minus k over x, and we want to evaluate this between 1 and 8. And if I set this equal to 112, for our upper limit, we have negative k over 8, and for our lower limit, we have negative k over 1. So we have negative k over 8 subtract negative k over 1 equals 112. And so if we simplify, we have 7k over 8 equals 112, meaning k is 128. Question number 4. The random variable x, which is binomially distributed with parameters 27, 0.35, part A for the first part, find the probability that x equals 10. From the main menu of your calculator, let's go to the distribution sub-menu. We have a binomial distribution. The type we have is an x equals. That corresponds to this option here, so click F4. X is equal to 10. The number of trials we have is 27. The probability is 0.35, and if we execute this calculation, you will find the probability that x equals 10 equals 0.1535, etc. So for the first part of part A, the probability that x equals 10 is equal to 0.1535, etc. For the second part of part A, find the probability that x is greater than or equal to 12 but less than 15. So, the probability that x is greater than or equal to 12 but less than 15, that is the same as calculating the probability that x is greater than or equal to 12 but less than or equal to 14. From our calculator, this corresponds to this type here. So click F2. Our lower limit is 12, our upper limit is 14, the number of trials we have still is 27, the probability is still 0.35, and if we execute this calculation, you can see we have this probability equaling 0.1794, etc. Historical records show that the proportion of defective items produced by a machine is 0.12. Following a maintenance service of the machine, a random sample of 60 items is taken and 3 defective items are found. Part B. Carry out a suitable test to determine whether the proportion of defective items produced by the machine has decreased following the maintenance service. You should state your hypothesis clearly and use a 5% level of significance. To begin with, H0, our null hypothesis, that's P equals 0.12, and H1, that's P is less than 0.12. And the reason for this is because we are looking at whether the proportion of defective items produced by a machine has decreased following the maintenance service, which is why we have the less than. Now, if we let the random variable d equal the number of defective items in the sample, d is then binomially distributed with parameters 60 and 0.12. Now let's find the expected value of x. For the expected value of x, that's equal to 60 multiplied by the 0.12, which is 7.2. Now, in the question, we know that 3 defective items are found. So what we are required to do is find the probability that x is less than or equal to 3. If we go to the distribution sub-menu, we have a binomial distribution. The type we have here is this one, and that's because the expected value is 7.2 and the 3 is less than the 7.2. So let's click F1. The number of trials is 60. X is equal to 3. The probability is equal to 0.12. And if we execute this calculation, you can see the probability that x is less than or equal to 3 is equal to 0.0601, etc. And because this is greater than the 5%, we can therefore conclude that this result is not significant, so we do not reject H0, which means there is insufficient evidence that the proportion of defective items has decreased. Part C, write down the p-value for your test in Part B. Well, for Part C, the p-value is quite simply this 0.0601, etc. And that corresponds to the actual significance level. Question number 5. A biased four-sided spinner has the numbers 6, 7, 8 and 10 on it. The discrete random variable x represents the score when the spinner is spun once and has the following probability distribution. So the probability that x equals 6 is 0.5, the probability that x equals 7 is 0.2, and the probability that x equals 8 and the probability that x equals 10 is q. And q is a probability. Part A, find the value of q. Well, we know that the sum of probabilities is equal to 1. So for part A, we've got 0.5, which is the probability of getting a 6, plus 0.2, which is the probability of getting a 7, plus q, which is the probability of getting an 8, plus q, which is the probability of getting a 10, and this is all equal to 1. If we simplify this, you will find 2q to equal 0.3, which means q is equal to 0.15. So q is equal to 0.15, which means the probability of getting an 8 is 0.15 and the probability of getting a 10 is also 0.15. Karen spins the spin repeatedly until she either gets a 7 or she has taken 4 spins. Part B, show that the probability that Karen stops after taking her third spin is 0.128. So for part B, if Karen stops after 3 spins, she must roll not 7, not 7, and 7. If we think about what this means in terms of the different outcomes, we could get a 6, and then a 7, or we could get a 6, an 8, and then a 7, or we could get a 6, a 10, and then a 7, or we could get an 8, a 6, and a 7, or we could get an 8, then another 8, then a 7, or we could get an 8, a 10, and then a 7, or we could get a 10, a 6, and then a 7, or we could get a 10, an 8, and a 7, or we could get a 10, another 10, and then a 7. So there's 9 different possibilities which we could have. And each of those possible outcomes are all independent of each other. Which means the probability that we stop after the third spin is the probability of not getting a 7 in the first spin times the probability of not getting a 7 in the second spin multiplied by the probability of getting a 7 in the third spin. Now, what is the probability of not getting a 7? That's 0.5 plus 0.15 plus another 0.15, which is 0.8. So we have 0.8 times 0.8 times 0.2. So we have 0.8 times 0.8 times 0.2, which is 0.128, and that's exactly what we wanted to show. The random variable S represents the number of spins Karen takes. Part C, find the probability distribution for S. If we let the random variable S equal the number of spins, the possible values for S are 1, 2, 3, and 4 only. Let's think about why that's the case. Well, it's because she spins the spin repeatedly until she either gets a 7 or she has taken 4 spins, so the maximum number of spins we have is 4. And what we need to consider is us either getting a 7 or we have taken 4 spins. So the probability that S equals 1, that's 1 spin only, and we stop at this spin when we get a 7, so the probability that S equals 1 is the probability of getting a 7, and that's 0.2. The probability that S equals 2, well, we don't get a 7 on the first spin, but we get a 7 on the second spin. So the probability that S equals 2 is equal to the probability of not getting a 7 times the probability of getting a 7. So that's equal to 0.8, which is the probability of not getting a 7, times 0.2, which is the probability of getting a 7, and that's all equal to 0.16. The probability that S equals 3, that's equal to 0.128, and we found that in part B. Remember, in part B, we don't get a 7 on the first spin, we don't get a 7 on the second spin, but we get a 7 on the third spin, and then we stop. Now, the probability that S equals 4, remember in the question, we spin the spinner repeatedly until we get a 7 or we've taken 4 spins. So we could have not getting a 7 in the first spin, not getting a 7 in the second spin, not getting a 7 in the third spin, but getting a 7 in the fourth spin, then we stop. Or we could not get a 7 in the first spin, not get a 7 in the second spin, not get a 7 in the third spin, and not get a 7 in the fourth spin, and then we stop. So there's two different ways we could stop. Not getting a 7 in the first 3 spins, but getting a 7 in the fourth spin, or not getting a 7 in all of the 4 spins. So we have 0.8 times 0.8 times 0.8 times 0.2 plus 0.8 times 0.8 times 0.8 times 0.8. So let's work this out. We have 0.8 to the power of 3 multiplied by 0.2 plus 0.8 to the power of 4, and that's equal to 0.512. So in terms of our probability distribution, we could either have 1 spin, 2 spins, 3 spins, or 4 spin, and the associated probabilities is 0.2, 0.16, 0.128, and 0.512. The random variable n represents the number of times Karen gets a 7. Part D, find the probability that S is greater than n. So for part D, since Karen stops after she gets a 7 or 4 spins, n can either be 0, that means spins 4 times and never gets a 7, or 1, so n could be 1, and that means spins a 7 and stops. So if we have n equals 0, that means when Karen does not get a 7 at all, and this happens when S equals 4, and we saw that in part C. When we have n equals 1, that means Karen gets exactly 1 7, and this happens when S equals 1, 2 and 3, and she stops because she got a 7. And therefore, the possible outcomes are S equals 1, n equals 1, S equals 2, n equals 1, S equals 3, n equals 1, S equals 4, n equals 1, S equals 4, n equals 0. So you'll notice that for all these events, S is greater than n apart from S equals 1, n equals 1. And you see that here. 4 is greater than 0, 4 is greater than 1, 3 is greater than 1, 2 is greater than 1. And in this case, 1 equals 1. So we want the probability of S equals 2, n equals 1, S equals 3, n equals 1, S equals 4, n equals 1, S equals 4, n equals 0. We want these. So the way we can get that, to find the probability that S is greater than n, we need to do 1 minus the probability S equaling 1, n equaling 1. And that way we get these probabilities. And what this will simplify to is 1 subtract the probability that S equals 1. And we know what the probability that S equals 1 is. We worked that out in part C. We found that to be 0.2. So we have 1 minus 0.2, which is 0.8.